I see time is 9:15, so let's start. So I would like to welcome you all to this public defense of Sujash Naskar's PhD thesis with the impressive name Privacy Preserved Authentication and Communication in Vehicular Ad Hoc Networks. Sujash has done his PhD here for 4.5 years under the EU regional projects called IoT testbeds and Digit, they are called the projects. I will shortly introduce the procedure, how it works, but first I would like also to present 4 other important members except for the respondent. And first I would like to introduce our faculty opponent, Professor Chunming Rong from University of Stavanger. He took his PhD at University of Bergen under the famous Professor Thor Helleseth. Everyone who knows works in crypto, algebra, information theory knows Thor Helleseth in that sense. And he is, your research is in cloud computing, blockchain, security, so he's very experienced in this area, so welcome. And then on our grading committee, from left here, we have Professor Lukas Wisniewski from Technische Hochschule Westfalen-Lippe in Germany. He is an expert in industrial IoT and digital communications as such. Then we have Professor Andreas Jakobsson from Malmö University, who is an expert in security and privacy for Internet of Things. And finally, we have Professor Mats Björkman from Mälardalen University, who is a professor and well-known in data communication. So these are 5 very important people today. And the procedure is that first the respondent will give a presentation around 30-40 minutes. Then we'll take a technical break, 5 to 10 minutes. After that, the opponent and the respondent will have a discussion here on stage. And when the opponent thinks he's ready and done with this questioning, it will be the grading committee who will take the turn. And when they are done and happy, we will open the floor for everyone else here in the room to ask questions. And after that, I will close this PhD defense. So before we start the presentation, I would like to ask you, Sujash, do you have some amendment to the thesis, or would you like to defend it as it is printed?
I would like to defend it as it is printed.
Okay, thank you very much.
Yes.
So then I leave the stage to you.
Thank you. Good morning, everyone. Thanks for being here today. My name is Sujash Naskar, and today I'm going to present my thesis, which is titled as Privacy Preserved Authentication and Communication in Vehicular Ad Hoc Network. So, right. So, I will start with an overview of what is a vehicular ad hoc network, what are the privacy and security challenges exist there, how authentication framework has been presented before, and what are the limitations in existing solutions that has motivated us to formulate our own research objective and research questions, how we have answered them and our contributions, the results we have achieved, and then finally some limitation of this work and towards future direction, and we will have the discussion session at the end. Moving forward, what is VANET? VANET stands for Vehicular Ad Hoc Network. As the name suggests, it's a specialized dedicated network or wireless communication for vehicles to communicate with other surrounding vehicles or with infrastructure. The primary goal of this network is to improve overall traffic management and overall vehicle-to-vehicle connectivity, as well as to reduce road traffic accident and improve passenger safety. It's a concept with a bigger picture of intelligent transportation system in smart city environment. So mainly there is 2 types of communication in VANET, vehicle to infrastructure communication or V2I, where vehicle gather information about local traffic data from infrastructure unit. And then there is another communication where vehicles share their speed, velocity, brake, this kind of information to other vehicles for driving assistant purpose. And for both of these two types of communication, vehicle uses a public channel. And as we all know, public channel have the influence of an adversary that can directly lead to public channel security attacks. Attacks such as reply attack, man-in-middle attack, impersonation problems, or civil attack, non-repudiation, typically all known public channel security attacks. And then there is also privacy issues. As vehicle communicate, their identity, their location traceability, their movement throughout the network can get leaked to unauthorized parties, and that's how privacy is a threat there. Now, to mitigate with these security and privacy challenges, authentication frameworks has been proposed. In existing authentication frameworks, there is typically two models, a centralized and a decentralized one. The centralized one assumes that all the vehicles and network peripherals in the network initially registered to a centralized CA, and that CA controls the whole network communication flow. Whenever a vehicle wants to be a part of the network, it has to do a mandatory authentication and get acknowledged with some keys that allow them to communicate with the others. And this is a typical model that has been proposed, centralized, but there is also a decentralized version for a more bigger application of VANET, for a large scale deployment, where they assume that all the vehicles are still registered to a certain authority called root certification authority, and the authentication part is distributed among sub-CA, which together with the root CA perform authentication. So that is what is typically presented and exists in the literature. However, there are some limitations in those solutions, and I will go through them. First, the security vulnerability. It is quite common to find reply attack, especially, and then impersonation problem, non-repudiation issues in existing model. Also, privacy leaks is easy to find. How? Messages from a particular vehicle in different time can be linked, and that's how it can link to a linkability or traceability issues of the vehicle throughout the network. That is a problem too. And then real-time authentication is important here. Why? Because vehicles share very critical information, speed, velocity, alerts, or braking info. So you need to execute the underlying cryptographic scheme, which is actually doing the authentication very fast to be real-time. But often the existing model rely on hard crypto logic, and that is quite time-consuming, and real-time authentication is not achievable. And then a revocation logic is big gap in the existing literature. Even after authentication, vehicle can do malicious activity. And then how you can revoke them from the system. This procedure, this logic, a functional revocation logic is missing also. And then single point of failure, as I discussed in the previous slide, they consider, even in distributed system, they consider a concept of root CA, which creates the problem of single point of failure, because something happens to the root CA affects the entire network. And that's how the communication bottleneck is there, even in decentralized models. And scalability is a big issue. As vehicles join the network grows, scale up, more and more vehicles, and then authentication framework has to deal with scale up with the number of vehicles joining. But existing model, because of the hard crypto logic or the way the control flow is designed, it is very common to see that they don't scale up if the network is very large. And all these things that I found and I read as the limitation of existing solutions motivates us to formulate my own research objective and research questions. So the research objective in one line can be said like this. We want to design computationally lightweight. That means the underlying cryptologic which is actually doing the authentication is very swift, fast and lightweight, robust. The framework could still work in unpredictable situations. And then you have highly scalable model, which means that it can scale up as more and more vehicle joins the network easily. And that, of course, has to be compatible with the resource constant and time critical nature of the VANET. And based on this objective, we have 3 research questions. The first research question is to improve the centralized authentications. So the question is, even being centralized, how can we accommodate a large number of vehicles in a centralized model? That is improving the scalability issue in a centralized model, while not hampering the privacy and security guarantees. So that is research question 1, to explore into centralized model. And then research question 2 is more towards distributed systems. How can we have a distributed authentication framework in VANET that doesn't have a single point of failure, that has a proper revocation logic, and that has improved the vehicle-to-vehicle connectivity to perform higher scalability? So that is towards decentralized and research question 2. And the research question 3, so far in literature, it has been assumed that 1 car per user. But in real life, 1 car can be used by multiple users in scenarios such as rental schemes. Now, how can VANET accommodate such rental or multi-user vehicle access schemes? And then how authentication, revocation will work? And that is something we wanted to explore in research question 3. So these are the 3 main research questions we formulated, and this figure represents how the publications are connected to the research questions. So we start with research question 1. We have, in total, we have 6 published publications. 2 of them are dedicated to answer the question, how can we have a scalable, centralized VANET, which being centralized can still accommodate large number of vehicles. And that is answered in paper 1 and 2. And then 3 paper is dedicated to more distributed authentication, as I said, with a proper revocation, no single point of failure, and improved vehicle-to-vehicle connectivity. And then the third question to answer, we have paper 6, which is multi-user vehicle access in VANET. I will have some, before I go to the question, I will have the assumptions made and the scope of this research. So whenever I mean authentication cost, I mean 2 things. Computation cost of the cryptographic logic to perform the authentication, and communication cost in message bytes. How much message byte you need to share to complete an authentication. These 2 things is mainly meant here, and there are other parameters or factors like physical channel latency or transmission latency. Those are outside of our scope, and I haven't considered them in considering authentication cost. And then we also assume that the trusted entity cannot be compromised, which is a valid assumption, and it has been assumed in all the other existing models. And adversary can attack the public channel communication. That is also the assumption, but they cannot compromise the trust entities. And for simulation purpose, we have used the OpenSSL and PBC crypto library. And for cryptographic security test, we have used the random oracle model for formal proof, and also the Scyther tool for the formal security validity. With this, I will jump into research question 1 again. Recall what was the question? It was, how can we make centralized authentication more scalable while ensuring privacy and security? So the way our approach is designed is to task distribution to local authorities. Instead of relying on centralized certificate in every communication establishment, you do some task distribution. Now I will explain in quick how exactly it works. So because it is centralized in nature, vehicles are registered to the authority initially, And now frequently whenever they want to be a part of the network, in each session they generate an authentication message that typically includes a hash proof that is randomized in each time, and this hash proof is sent to the CA through the roadside unit available to that area. And once verified, a pseudonym which is defined as random identity for that vehicle for that particular session of communication. And this pseudo identity is generated and shared with the vehicle which is requesting for an authentication and the roadside unit which is coming, the request is coming from secretly. So at the end of the authentication, a vehicle and its closed by RSU will have a secret pseudonym. Now we use this pseudonym to establish a vehicle-to-vehicle communication directly in token sharing approach and exclude the CA's involvement here because we already established a pseudonym between them. And what happens here, a vehicle do a one-time token sharing by the help of the roadside unit. It shows a hash proof against its pseudonym and allow the vehicle to share the token with others, and then they can have a direct communication. A token could be symmetric key for signing messages or encrypt, so on. So the novelty here is that removing the CA's involvement in each communication establishment, which is typically found in existing literature. That's the novelty, and we perform this using only hash operations, which is very lightweight crypto operation. Now if we go, as we said, authentication cost in terms of communication and message byte. So we simulated with the crypto library we chose. So because we have used hash functions which is cryptographically lightweight, we can perform verification for each vehicle in a fraction of millisecond, comparing to the other which rely on elliptic or bilinear pairing, which is computationally more time consuming than performing hash operation. And that directly help us to have a higher authentication bandwidth, which is if you have less time to execute one authentication, for a given time you can perform much more. And that is exactly how we scale up the centralized model to accommodate large number of vehicles to get authenticated, even being centralized. So that's the contribution made that we achieved also real time, we can conclude, because it is less than a millisecond to perform one vehicle authentication. But one can question, if you have used only simple crypto such as hash, how do you prove security here? For that, we have given a random oracle model based formal security proof with this equation. I will not explain every term here, but a quick overview, what is this equation presents. Left side ADVA presents the advantage of the adversary to break the system is same as breaking the right hand side, which presents breaking the hash collision probability or pre-image resistance property of hash function or quadratic reducibility assumption, which we also used in this model. And these cryptographically hard problems are proved to have no feasible solution in polynomial time. And that's how our scheme is provable against polynomial time. And that's how security proof is given. A quick recap to research question 1. High scalability is achieved because we can accommodate large number of vehicle authentication. Fast real-time authentication because less than 1 millisecond per vehicle to do authentication, and for privacy, no traceability. Because we used randomized pseudonym, randomized hash proof, each time an authentication request for each session is different and unlinkable than the other one. And that gives us no traceability of vehicle and preserve vehicle location-based or identity-based privacy in the overall network, even from RSUs. However, because the model is centralized itself, there are some limitations. Limitations that are not a fault of the presented scheme, but internal limitation of a centralized model. Anything happen to the central CA affects the whole network. So we need to move towards more distributed and decentralized model. And also for a more bigger inter-regional application such VANET could have, we need to move forward with more large-scale deployment in decentralized models. That's how exactly our research question 2 is designed. How can we have a truly distributed decentralized model which have, again, recap, no single point of failure, and then have a proper functional revocation logic if vehicle do malicious activity, and have improved the vehicle-to-vehicle connectivity for scalability. Okay? So, first thing we did is to present a distributed system model for VANET, which is a bit different than existing system models in distributed architecture in VANET. So, I will explain it with a simple example. Consider a country which have many states. Each state have their own certification authority, and together collaboratively they run the whole country's VANET network. Now, each state can have many local verifier that is connected to their region specific CA, and vehicle can get locally verified from this local verifier. So, that is how exactly this model is presented, our model. The novelty of this model, system model, is that we do not have a root CA concept here like existing I said. Vehicles are not considered, or doesn't have to, all vehicle in the network doesn't have to be registered to a single entity. That is exactly what the bottleneck is. So, we want to remove that part, and that is the novelty of this model. And the concept of locally verifying vehicles is also something new, and we have proposed it in this model, and this also allows for a large scale deployment in VANET, as because it is truly distributed in nature. Now, how authentication work in this model, that I will explain in this figure. So, flexible registration, because we do not have a root CA, vehicle can register to their regional specific CA. Whichever region the vehicle belongs to, it registers, and that CA becomes its parent CA. Once registered, now vehicle could become a part of the network by doing this session-wise verification. So, verification is designed on a public infrastructure which is dependent on elliptic curve digital signatures and generating randomized certificates. So, whenever vehicle want to join the network, it creates an authentication request which is a typical randomized digital certificate, and with the help of the proposed algorithm 1, vehicle can get locally verified without each time the verifier communicating the CA. So, A to B, B to C, no. We propose A to B, and that is vehicle to the verifier and the response from verifier to vehicle to minimize the communication. And that is how local authentication is proposed. And at the end of this verification process, each vehicle now holds a certificate that is signed by the local verifier, which means that it can show its legitimacy holding this certificate to other vehicle and communicate directly. The other vehicle, using the algorithm 3 which is proposed, can directly verify the validity of the certificate in current session and can communicate directly. That is how direct vehicle to vehicle communication is established. No help of LI or CA is needed, direct help is not needed. Now comes the revocation part, which is missing in existing model. How do you revoke a vehicle even after it has been authenticated in the system? Vehicles are malicious considered in this network. So, even after getting verified, they can send malicious messages to the others. In that scenario, in our case, because each vehicle have a certificate that proves their legitimacy, any, let us say, victim vehicle can generate a report that consists of the certificate of the malicious one and the message it has sent that has created a dispute. And this report is sent to the verifier. And then the verifier's job is to first verify the legitimacy of the report, if no one is trying to framing someone first. And then if the legitimacy of the report is correct, the certificate of the malicious vehicle can be revoked from the current session. And that is how propagation of malicious message can be stopped. And further, the verifier can let the connected CA know about this revocation, so that this vehicle can be revoked from the entire system in a synchronized way if necessary. So this is a functional and synchronized revocation based on this PKI infrastructure is proposed in this model. And then another thing, vehicle can move between regions, and that's how the new region need to get initialized for the vehicle specific authentication parameters, and a handover protocol is proposed here to allow vehicles for interregional transmissions. With this, the first authentication framework in a distributed structure has been proposed, answering what was our questions before. But we found some area that could be improved, especially vehicle changing the regions where explicit handover request was needed, as I said before. So one can question if vehicle has to determine when and to whom and how to do authentication, it puts some level of computation on the vehicle side. But the overall goal is to minimize the vehicle computation and put it on the others. So let's not have explicit handover from the vehicle. Vehicle should just send authentication request no matter what region it is. Another thing, having explicit handover could create privacy issue when there is only one or two vehicle in such a region where the influence of many verifiers exist. And then if imagine is one or two vehicle, then it becomes somehow obvious who did handover and which region it has entered. When it's multiple or many, this problem is less, but for a number like one or two, it could be an issue. So let's remove explicit handover when vehicle change region. And that's how another authentication framework has been presented in paper 4. And here we took help of the non-interactive zero knowledge proof based on elliptic curves here. So each time vehicle generates a request, which is a randomized zero knowledge proof encrypted, and also vehicle encrypts its parent CA information and send it to the local verifier available. Local verifier can decrypt only the zero knowledge proof part, and if the shared secret exists in its database, can verify it locally and sign the certificate like before. However, if the shared secret is missing, then comes the handover part, let's call it. So the LI now forward the request to the connected CA, which can decrypt the parent CA information of the vehicle, and then collaboratively, if it is the parent CA, it shares the hashed version of the secret to the verifier, or if the other CA holds the secret, it acquires it and sends it to the LI. So you can see somehow this, in this part, handover is done, but not from the vehicle side. Vehicle always generate this request and send it. It is up to the verifier's job to acquire the authentication parameters for the first time. And this is how the novelty is. No explicit handover is needed in this case. And now, what about the cost? So when we have simulated, because we have used elliptic curve based crypto logic here, the authentication per vehicle is around 2 milliseconds. And if we compare it to the existing model who try to solve it in a decentralized way as we have tried, recall they don't have the same facilities as we have done, but still they try to implement it using bilinear pairing mostly in existing solutions. And because of their crypto logic, the control flow, they have higher authentication time in execution point of view than ours, which gives us 5 to 16 times faster execution, more or less, if we compare. And because we have less time per vehicle, you get a higher bandwidth to accommodate large number of vehicles than the other ones. With this, the authentication part is answered, how vehicle to infrastructure authentication has been done. Now come, and also the revocation part. Now comes how do you improve vehicle to vehicle connectivity. This is authenticated, but after authentication, as I said, now vehicle show their legitimacy to others and communicate. And that part can be improved as well, and it has to be improved. Why? Imagine a scenario when one vehicle is surrounded by many vehicles, and they are sending speed, velocity, brake, this kind of information with each other. So one vehicle can receive large number of messages in a given time, and each of these messages contains time critical information, and they have only 300 millisecond lifetime for each message. So if you go with a single standard verification where you individually verify each of the received message, you can risk message expiration. By the time some of them get their chance, maybe they expired the 300 millisecond threshold. That's how the batch verification concept has been brought into vehicle-to-vehicle connectivity in VANET, where the concept of batch means that group of messages getting verified in one go. And that is cryptographically possible, and that has been proposed in the literature before, and we also proposed ours, but we have to understand what is the difference between them and how we have improved it. So existing batch verification doesn't consider that in each batch there is only clean message. That's how they consider their batch verification, which means messages are not corrupted in transmission or maliciously altered. And this is something which is not realistic. If you consider a batch only with clean message, then what happens if there is a wrong or maliciously altered, or it could be transmission error on a message? Then what happens in existing solution, the whole batch will be rejected. So even if one single message is wrong in a whole batch, the whole batch they reject it. They only accept it if all the messages are clean. And that is something that creates a limitation, doesn't reflect a real scenario. And these messages you cannot just reject because they can hold critical information. So our goal was to have a batch verification in such a way that in case of verification of whole batch fails, it could filter the good one from the bad one in an efficient way without being more computationally heavy than performing individual verification. So that is exactly our novelty. You consider that each batch have faulty messages in them, and then try to filter good and from the bad one in case the verification fails without being worse than performing them individually verified. And this result shows how much efficiency we have got comparing to individual verification. It gives a lot of information, but I will just choose some part of it. The x-axis presents how many messages gets verified within this 300 millisecond given time. Y-axis present how much portion of the message in each batch have error. Like 10% message in the batch have error, 20, and so on. And then we compare for our scenarios with the standard individual verification, which is orange line. Standard verification, they individually verify, so they have a constant number for a given time, and that is 200 message that they can do in 300 millisecond time. But based on exactly where the wrong messages or invalid messages are located in each batch, we have three cases: best, average, and worst. And I will pick the worst case scenario here to show that even in worst scenario how much efficiency we gain. So we can see that as error increase in the batch 10%, 20%, when we have 10% less than 10, we achieve much higher number of messages getting verified by the vehicle comparing to the 200. And then as the error increased, when 40% of message in each batch have error at that threshold, we achieve same efficiency as standard verification. But again, 40% of message in each batch is a lot. And then one can question, should we still trust the channel or not? So there could be some questions there, but we can accommodate even 40% error per batch in worst case scenarios. And that is exactly the contribution which is pointed out in these bullet points. Now, again, recap research question 2. So we have proposed a truly distributed model which have no single point of failure, and authentication is locally distributed. We have achieved high scalability because the computation is low cost, and then a synchronized revocation is proposed for vehicles to stop malicious activity even after authenticated. Then we have presented a no traceability because we have used randomized certificate, non-interactive zero knowledge proofs which are also randomized each time. Vehicle identity traceability, location traceability has been removed, and then improved vehicle to vehicle communication because of this fault tolerant batch verification model. So vehicle can accommodate much more message than existing models. Now, what are the limitations? What can we improve more? So that's exactly what research question 3 does. Even now, we have considered one vehicle per user. What happens if we have one vehicle multiple user to reflect scenarios such as rental schemes? So we need to answer research question 3, which is how the authentication framework will work or how it will change to accommodate such application. So here in this model, on top of the authentication part, we have 2 more protocols. First, there is owner of the vehicle and the valid user. They need to come to an agreement, which is a digital certificate signed by both sides, that allow an user to use the vehicle by performing a challenge response protocol with the vehicle. And now a user can be the owner itself as well. So the protocol is designed based on who is using the vehicle. And with this challenge response protocol, once the current user get access to the vehicle now sends authentication message to the network like before, encrypting zero knowledge proof. It also encrypts the current identity of the current user. And why? Because in case this vehicle gets to a dispute, there has to be a way that the CA can decrypt the original identity of the current user and take it accountable. That's how revocation could be done. Because at different time, a multi-user vehicle can have different user, and you need to account the one which is current user. And then, okay, what is the novelty then? This is first of its kind. No one before has proposed how authentication will work in VANET accommodating rental or multi-user scenario, and the contribution that it indirectly improves vehicle accessibility, one vehicle multiple user, as well as allow direct accountability to the current user. So with this, I will say that all the 3 research questions we have tried to answer. Now I have showed the solutions, their novelties, the contributions that have been made, the results we have achieved. Some conclusions. So optimized centralized authentication, the first research question, 1 millisecond per verification that we have achieved, which is we can conclude that real time. Privacy preserved distributed authentication. We have removed the single point of failure, used elliptic curve digital signature or non-interactive zero knowledge to achieve this. Functional revocation method, which was a big gap, as I mentioned. We have tried to show how revocation can work in VANET to stop the propagation of malicious message from the network, improve vehicle to vehicle connectivity with a fault tolerant batch verification model, which reflects more realistic scenario as it consider error messages. And then we have proposed also role based multi users in VANET such as rental schemes. There are some limitations of this work. Limitation that doesn't reflect internal fault of the proposed scheme, but the scope. So we have seen the security privacy issues from communication point of view only, but there is way more security challenges to consider outside this box, such as how data are handled, how data storage will be done, how secure routing protocols could be implemented. This kind of thing need more research, and they should go together with this kind of authentication framework as well to have a fully reliable and trustworthy VANET. And then validating the result with real-world test. Our test is computerized. Now, if you implement it in a real vehicle, how actually these things work would give more insights. But having such an infrastructure it outside, but maybe in future, and also fail-safe extreme condition models. For example, what if part of the network go into blackout? Then how you secure the system? So more fail-safe model needs to be developed as well. So these are future direction. Starting from there, and you improve the model to accommodate these things. And about research ethics, I must mention, we have followed all the academic research ethics throughout the research. Principle of integrity, reliability, honesty and of data collection and reporting, credits and guidelines of publications has been followed. And we have not used any sensitive information of individual or organization, so social considerations are made. With this, I will conclude today's presentation. Thank you for listening, and I will go back to Mika.
Thank you, Sujash, for the presentation. We will take a short technical break, around 7-8 minutes, and then come back with a discussion between the opponent and respondent. Thank you.
Thank you.